Venkat, please check it. Am I audible?
Yes, you are audible only, ma. She has unmute and.
No.
Okay, now I think she is able to hear your voice.
So I already given co-host to the ma'am, sir.
Okay, now I think she will speak. You once again call. Using the line only. Madam.
Ma'am, I think she has some network instability, ma'am.
Okay. Then shall we start, sir? Then.
Yes.
Okay. Very good evening to one and all gathered here. I welcome you all for this day 3 of Photovoltaics 360 design to implementation. We hope you are all fine and safe. From the past two days, we have been enlightened with photovoltaics in synthetic as well as the fabrication aspects. These are all the live clips we have taken in the day 1 session. So as like today also, I request all the participants to enable your video to take the live snap. Venkat, please enable the participants to unmute their video.
Okay, ma'am. Okay.
I'll stop sharing the screen first. Okay.
Participants, kindly open your camera.
Smile, please, all of you.
Participant, please kindly open your camera. Yes, ma'am. Done, ma'am. Done.
Okay. Thank you, Venkat, and thank you all. I'll share my screen again. Just a minute. So before moving to today's session, I would like to address the query raised by, I think, Mr. Rajkumar in the yesterday's session, which is related to the role of photovoltaics in electric vehicles. So you can see from this slide, from this academic year, our present has introduced a minor degree program for BTech students in electric vehicles. So that you can see here, the courses offered in this minor degree program is energy devices for electric vehicles. So it is absolutely yes, definitely there is a role of photovoltaics in electric vehicles also. Okay, so for more information, I request the participants to kindly go through our institute website, which is www. Am I audible, Venkat?
Yes, ma'am. Yes, audible.
Yes, ma'am.
Yeah, okay. So this electric vehicle course as a minor degree, so definitely there is a scope for the photovoltaics in electric vehicles also. Okay, so moving to today's session. Today's session is related to the theoretical inputs in photovoltaics designing. It is observed from the literature and reviews, theory and experimental part of any field of research. It has to go with the hands together. I feel like there should be the a perfect collaboration between the experiment as well as the theory, including the facilitation of effective communication and to address the navigation of problems that arise in which field whatever we are working. So we thought of including as a session specifically for theoretical insights from DFT calculations in this photovoltaic webinar series. So with these few words, I hand over the session to today's chairperson, Dr. A. Sajan sir, Associate Professor of our Chemistry Department. And for today's session, the moderator is Dr. K. Karthikeyan, Assistant Professor Senior Grade of our department, BSACIST, Crescent Institute of Science and Technology. Sajan sir, please take over the chat. Thank you.
Good evening. Audible, madam?
Yes, yes, sir.
Good evening, everybody. I'm very happy to welcome for this 5 days webinar series. It is the third day of this webinar series. Every day, professors and scientists from various institutions are coming and addressing. Today, Dr. Madhavan Jacob, Assistant Professor, Department of Chemistry, Scientist, Computational Chemistry Laboratory, Loyola Institute of Frontier Energy, Loyola College, will address. I'm welcoming all the participants in these occasions. And also happy to introduce today's speaker, Dr. Madhavan Jacob. Dr. Madhavan Jacob completed his PhD in theoretical and computational chemistry from the Department of Chemistry, Bharathasan University, Tiruchirappalli, Tamil Nadu, in 2011, under the supervision of Professor P. Venu Vanalingam. He visited as a visiting research scholar at Professor Peter Hampa Research Group, Institute of Inorganic Chemistry, University of Heidelberg, Germany. Then he joined the group of Professor Gopalan Rajaraman in Indian Institute of Technology, Mumbai, as a postdoctoral fellow. He joined as a faculty in National Institute of Technology, Tiruchirappalli, for 6 months. Then he moved to permanent faculty position in the Department of Chemistry, Loyola College, Chennai, Tamil Nadu in 2013. His research interest in the modeling of reaction, intermediate and transition state involving bioinorganic and organic reactions, and design of molecules for novel optoelectronic device and for solar cell applications. He is also interested in studying the mechanistic aspect of small molecule activation and hydrogen evolution reactions. He was the recipient of DST Aspire faculty and DST Fast Track Young Scientist Award. He has published 54 articles in international, well-reputed, peer-reviewed journals, and 1 book chapter, Royal Chemical Society, Chemical Modeling, he published. He is also an active author of Quantum Chemistry, textbook authored by Ira N. Levin, 7th edition. He has completed 3 major projects with the tune of 83 lakhs. Such a qualified, such eminent persons with us. I once again welcome Dr. Madhavan Jacob sir. I welcome sir. We are going to present today design of organic dyes for optoelectronic devices, insight for TFT calculations. So I will once again welcome everybody for this webinar, and also I hand over the mic to Dr. Madhavan Jacob. Sir, Madhavan Jacob sir, welcome sir. Now we can start.
Thank you. Thank you for your nice introduction. First of all, I would like to thank organizer for giving me the opportunity to present and share my experience in the field of photovoltaics. Okay. So now I'm going to share my screen.
Yes, yes, please.
Is it visible?
Yes, yes, slides are visible. Please make it a slideshow.
Yeah.
Yes, please go ahead.
Thank you once again. What I am going to talk today, it's all about, I am a theoretician. I'm a complete full-fledged computational chemist where I use all kind of techniques in terms of doing computation rather than performing experiments in the laboratory. Okay, that's what my specialization. Before I'm going to talk about my present discussion, I just to give you the overview about whatever the topics I'm working on. I'm much more interested in doing modeling chemical reaction and investigating their mechanism. That's my PhD area where I have completed two different areas where inorganic chemistry, especially bioinorganic and organic reaction mechanism. The last one, the studying non-covalent interaction, drug designing, and their property, how they are host-based complexation, how the host-based complexation influence on the electronic structure of the chemical molecules. In addition to that, right from 2013, I have collaborated with one of my friend who is actively working in designing sensors, optoelectronic materials, and efficient dyes for dye-sensitized solar cell. So in which I have started my research on collaborating with the experimental person. These are all the bibliometrics only related to optoelectronic material where after starting my collaboration with a well-known friend, so we have published more than five papers in ACS, 8 papers in Royal Chemical Society, and another 6 papers in elsewhere. All are the aggregate of impact factor also is given. Okay, so before I'm going to talk about whatever I have learned through the collaboration with the experimental guy, who is nothing but Dr. A. Kadiravan. He is recently a SCRB research scientist and he joined in Welltech. Earlier, he was in Madras University, Ultra-Fast Center for Research, where he was working as an Inspire faculty fellow. So I thank, and also I am dedicating this presentation to Dr. A. Kadiravan, because whatever I'm going to present today, that those things I learned from Dr. A. Kadiravan in order to support his experimental observations. Okay. What are the need? Actually, what are the need for doing computation in terms of computational spectroscopy? Because you know, all the experimental observation, we need the confirmation in terms of spectroscopic information. You know, spectroscopic is a fingerprint of the molecular system. Once you need to confirm whether the particular product is formed or the reaction is completed, everyone will take the NMR or IR or UV, depends on their availability, the instrumentation, all the things. They will take IR and the UV and then try to confirm their product formation. There are a huge indirect information which is available in the experimental spectra, where these interpretation is vastly different from different people based on their observation, purely based on their knowledge. You know, the knowledge is purely based on their fundamental knowledge observed in their particular field. So very important to interplay several different effects, especially as you know, when you come to the molecular spectra, there are rotational, vibrational, and electronic. Energy levels are interrelated. Ultimately, you have the broad spectrum. So that's what we need to have the clear-cut idea. In order to do that, we need to compute the spectroscopic properties. It is specifically useful in terms of two different levels. What are they? One is supporting and complementing the experimental observation to determine the molecular structure of the target molecule, starting from its spectral property. Second one, dissecting and evaluating the role of different effect in determining the observed spectroscopic property. This is what we differ from experimental, where I can easily pinpoint from which part of the molecule is responsible for the particular transition. That's what the dissecting and evaluating the role of different units present in the molecule. Okay, before I'm going to talk about my lecture, you have to know the popularity behind the DFT functional. You know, the DFT started from 1939, which is less popular. So there is no that much popularity. After Consam and Popel got the Nobel Prize in the field of DFT, there are huge popularity in publishing paper with the DFT. These are all, you can see last year I have taken the Scopus analysis report, nearly 1,93,719 documents has on published in terms of using DFT. These are all the area, these are all the countries in which the DFT is much more popular. You can see here number of publication in country wise, where China and the US are often using most of the their publication by using DFT. India is also publishing more than 12K publication in every year. Okay, this is a particular analysis report where you can see the subject wise. You can see how much the chemistry is influenced in terms of using DFT, 30.7, as well as material science. It's roughly around 30, 50, 60, 70% of the theoretical or experimental work is based on or utilizing the density functional theory in their research work. These are all the people who invented DFT, especially the Walter Kohn and Popel. They are the pioneer in the field of DFT, where they given the proof for DFT, exactly how the ground state electronic energy can be predicted by using the density of the molecule. So as you know, recently, these are all the people got the Nobel Prize in chemistry by utilizing the multi-scale model for complex chemical system using computational based calculations. So as you know, everyone afraid about studying quantum chemistry. As you know, there are complex behind physics, maths, and chemistry aspect, especially how the electrons are moving in the molecule. When you come to consideration of electronic structure of benzene, as you know, there are 42 electrons. 42 electron has to be considered as 126 coordinates. You know, the molecules has to be considered in terms of X, Y, Z. That is a Cartesian coordinate. Obviously, you need to the 3n coordinates as well as 42 electronic spin component. I'm not going into the detail. If I go into the detail of exactly quantum chemistry, nobody will be interested on my talk. So I'm going to give you the idea about how to do the calculation. What are the things needed to be concentrate on performing the calculation. But when you consider density functional theory, you need to have only 3 coordinates. That is a density. Okay. So these are all the inception from DFT. These are all the people who given the tablet form of or software form of DFT functional in Gaussian or anywhere. So Walter Kohn, the emeritus professor of physics, and then Kornberg, he is also from USA, Sam. These are all the people pioneer in terms of DFT development. As you know, how the DFT is popular by citing these 2 people paper, which is published in Physical Review in 1964 and 65. So how the DFT is very useful in terms of studying the electronic structure of matter, especially how does atoms, molecules exist in the particular molecular geometry, and what property, how the ground state energy and electronic density varying upon changing the molecule, and what are the bond lengths and bond angle, nuclear vibration. So how much energy needed to ionize the atom or molecule or the break wave bond. These are all the things. You know, interesting phenomena everywhere. When you talk about all the molecule, when you come into the picture, very minute way, the hero is electron. Whatever you say, even cellulose, even you take wood, you can take any number of material in a bulk manner. The major component present in those, all the things, whichever you are looking at in the screen, that is purely based on electron. See, this electronic treatment in terms of quantum mechanical way, that is very complex. Okay, so now I'm going to give you the overview. So from which basic introduction, what I try to convince you, there are three important things. Now, today everyone is utilizing DFT functional for their research work. But how to do? What are the essential ingredients or information needed to be retained when you perform the theoretical calculation? That's what very important. Everyone can cook, everyone can eat, but how they are eating, how they are cooking. Similarly, what are the things we need to follow when you do the theoretical calculation? Okay, theory is the general explanation of particular phenomena that has withstood many attempts to disprove it. But model is anything. You can take any kind of model as you wish. When you ask me to draw a cat, I can't exactly pinpoint whatever the way the cat looking. I can draw whatever the way I can pinpoint. That's what model. So model is a introduction of simplifying approximation into a more general theory like VSEPR theory. You know, this is a fundamental in terms of representing the molecular geometry. Even when you try to fix the hybridization of the molecule, we need to know the valence shell electron pair repulsion theory. Okay, what is computation? This is just action of mathematical calculation. When you use a computer in terms of doing the mathematical calculation, that is what computational chemistry or computation. It permits existing theory to be applied to increasingly complex system to better gauge the degree to which they are robust. This is what I'm trying to focus. So it is a use of digital technology to solve the mathematical equations defining a particular theory or a model. So what is the difference between theoretical and computational chemistry? Theoretical chemistry is a mathematical description of chemistry. It is often synonymous with the quantum mechanics. That's what the people are afraid about quantum mechanics. This is just a theoretical chemistry. But what is computational chemistry? Computational chemistry uses existing computer software to study the problems from chemistry. Okay, so what specifically when you generalize? Computational chemistry use a mathematical method which is sufficiently developed in and it automated in a computer. This is what the difference between theoretical and computational chemistry. What is meant by molecular modeling? Molecular modeling is a discipline concerned with the developing models of molecular system, chemical reaction, and the phenomena of any interest, whatever the interest in terms of chemistry. So what we are using often in molecular modeling, we are using the theoretical method and the computational technique to simulate the behavior of molecule and the molecular system. This is what we are doing. So especially we are trying to represent the behavior of molecular system in an electronic environment. Okay. So why do chemistry and computer? Complement and alternative to the lab experiments, especially investigate the unusual temperature and the pressure conditions. I can use a cyanide, n number of cyanide, any n number of poisonous chemicals. I can simulate the dangerous experiments and alternative method for hazardous, gain an atomistic description of reaction, save the enormous amount of cost utilization, and understanding the reaction mechanism by characterizing the reactive intermediates such as transit state, which could not be characterized by experiments. And as well as we can easily identify the rate determining step and the controlling tuning of the chemical reaction. We can give the rational drug design property calculation. This is what especially conformation interpretation of experimental results, prediction of new result, but everything is based on experiment. We can't go beyond experimental. We have to follow the experimental data where the final correlation done with the experiment. So these are all the advantages as I already discussed. These are all the properties, the wide range of properties we can calculate. So what are the accuracy in terms of comparing the molecular structure, plus or minus 1%, reaction enthalpy, plus or minus 2 kilocalorie per mole. These are all we benchmark, people already benchmarked with the available functional and basis set, and they given. Okay. So what are the major conceptual method in order to do the theoretical calculation? One is the validation with the experimental data, interpretation of the observed result, whatever you computed, and then prediction for the future experiments. Whatever, give us insight, not numbers. This is a very famous quote by C.A. Coulson, where the insight can be differ from different people. The number is same. 1 plus 1 is 2. But how you are interpreting, that is very important in terms of doing the computational chemistry experiments. It is absolutely essential that we know how accurate our computer result, first one, and then how you are going to utilize, how you are going to interpret your things in terms of right reason for right answer. So celebrated target accuracy is the chemical accuracy within 1 kilocalorie, that is obviously 4 kilojoule per mole in terms of energy. This is what we are trying to do. I'm choosing the chemical or physical problem, whatever it may be. It can be a chemical reaction, it can be a photophysical property, it can be a non-covalent interaction, it can be a post-waste interaction, or it can be a drug designing, anything. We can do the molecular simulation. And then modeling data. I did the modeling, I got the result, and how I am compare with the experiment, that is a validation, and then how you are predicting in terms of giving the insight on the number and try to give the prediction. This is what we are basically doing. Okay, my dear participants, here I am trying to give you idea about how one can perform the theoretical calculation. What are the things you need to do? Even you try to start your calculation right from the moment when you have the facility in terms of high-level computer for a, say, workstation, the small workstation which is having the at least 2 TB RAM, and then you can start with some software, Gaussian, that is a perpetual license which costs around more than 10 lakhs, but you can use it for longer lifetime. Okay, so what are the flow chart in order to do the calculation? Number one, when you try to do any modeling, any computational calculation, the first ever thing, you need a molecular geometry. Okay, I will explain how to represent the molecular geometry in computational software. These are all the various methods of representing the molecular geometry, and then graphical or hand. Earlier we wrote the internal coordinates when I was studying my MSc. I will use I can write the coordinates for benzene and try to do the MOPAC calculation, which is freely available. That software is also freely available. You can do the thing, and then we can use a many program, the Amber, Gromax, Charm. These are all which is specifically used for docking, the molecular drug design. These are all the Gaussian, Gammas, MolPro, MOPAC. These are all DFT calculation quantum mechanical program, and then we can deduce the molecular property, then we will interpret. We can deduce whatever the molecular property in terms of structure, energies, molecular orbital. So how the molecules can be represented? There are, as you know, these are all very fundamental thing, as you know very well. Graphically, when you represent ball and spoke model, and then Sagar's model, Newman projection, everything you can do, whatever the way you can study in your the college level, especially undergraduate level in stereochemistry. You can see the electrostatic potential where the more nucleophilic and electrophilic site can be easily observed from the molecular orbital analysis by computing their wave function. These are all the basics of computational theory where often we can use. This force field is very, very fast. This can be used for drug designing. Quantum mechanics, this is a very accurate, reliable when we compare with the other two methods. We are using often DFT. So DFT, it is computationally intensive than other method, but we have to use small benchmarking. We have a lot of functional, which is used to compute the molecular property as well as the basis set. I'm not going into the detail about what are the functional and the basis set. That is not my focus of my study, present discussion. So I'm just to touch on the functional and the basis set. Okay, as I told you, these are all the accuracy depends on time. When you spend lot of time, the accuracy depends on how many atoms you are taking. Smaller the atom molecule, accuracy will be much more because you are using the higher accurate method in terms of getting the molecular property. So quantum mechanics, that is a DFT or Hartree-Fock method, accurate, can deal with the reaction, parameterize with the force field, and then we can easily doing the things, but it is time consuming for molecules. Okay. So these are all the Schrödinger wave equation, as you know. This is Hamiltonian. Hamiltonian is nothing but everyone is unaware of these things. But when you studied in your college level, even school level, people are aware of that. What is Hamiltonian? The other way it is known as total energy. Total energy. Total energy is nothing but everyone can say, even 6th standard student will say, total energy is nothing but kinetic energy plus potential energy. Kinetic energy is nothing but half mE squared. Potential energy is mgh. See, when I take this pen and throw it away, this is, if you imagine, this is a electron. I'm giving some kinetic energy, some force. I'm throwing out. What is the thing is happening? Some energy lost or energy gain is occurring. That's what this E. This is psi. I'm retaining the same function. This is what simple Schrödinger wave equation is illustrating. But when you ask the people who studied quantum mechanics, what is Hamiltonian? They are thinking that something from heaven, it landed, and we are unaware of these things. Simple. The electronic energies is written in terms of wave function, and we are operating those electronic wave function. We are giving some force in terms of energy and try to get the eigenvalue or eigenfunction. That's what in order to solve this equation, we are scanning the particular distance. Where when you scan the particular distance of the molecule from, for example, when you take CO double bond, CO triple bond, I think. CO triple bond for normally 1.25 Armstrong. Ultimately, what will happen? It will be nothing but you are varying the angle by 0.05 angstrom. Upon varying 0.5 successively, you will find the some most stable geometry where it is having the equilibrium bond distance. This is what Morse law where we often do this. So what is terminology which is present in the computational chemistry? That is nothing but potential energy surface. Potential energy surface, you know, global minima, maxima, saddle point, transient state, stationary point. There are so many terminology. What is global minima? Minimum, the minimum amongst all the minima. That is a next one. And this is what the global minima. These are all local minimas where they can be a saddle, they can be a transient state. These are all the points where we can come across. Okay, together minima, maxima, saddle point or stationary point where the molecule can land. Okay, there can be any stationary point that corresponding to one geometric parameter. So global minima, it is the lowest energy point anywhere on the potential energy surface. How do you calculate? By computing the frequency. Frequency is nothing but the degrees of freedom. As you are aware of that, total degrees of freedom 3n. Each molecule have the 3 degrees of vibrational freedom, rotational freedom, 3 translational freedom. So obviously, for linear molecule, the molecular rotation will not be accounted. So that for linear molecule, it is 3n minus 5. For non-linear, it is 3n minus 6. This is what often we come across. Okay. So as I told you earlier, this is a potential energy. That is a kind of Mott stretching, bending, everything. Kinetic energy, we often compute this. This will be related to vibrational motion. Single point energy, it is a common terminology we often use in computational chemistry in order to get the accurate energy of the molecule. So we often do the only compute the electronic energy or the especially potential energy of the molecule on the fixed point. Okay. So what way we can mention the coordinates when you try to compute the molecule? Okay, there are 2 ways. One is the Cartesian coordinate, another one is the internal coordinate. As you know how to write internal coordinate, for example, hydrogen molecule, you take, I am having 2 atoms in hydrogen molecule. Okay, very clear. The first hydrogen I am fixing, it's a reference, and the another hydrogen I am taking with reference to this hydrogen, it is connected with the 1.1, 1.0 angstrom. If it is exact, then I can put 0. If it is not exact, I can put 1. Then I will run the calculation in MOPAC. I will get the atomization energy. Similarly, we can write it for larger molecules. This is what I did it when I was doing my MSc project. I did up to naphthalene, anthracene. I wrote the internal coordinates. But the Cartesian coordinate, as you know, when you try to represent the molecule, we need a point, 3 points. Especially when you mention this pen or laptop, I kept a laptop on my table. So I'm representing. Similarly, in order to represent the molecule in terms of plane, you need a 3 points. That's what X, Y, Z. That is given as Cartesian coordinate. This is the internal coordinate. As I told you, length, angle, that is a third atom which is coming to the picture, angle. If it is a fourth atom, it is a torsional angle, that is a dihedral angle, the angle between the 2 planes, intersecting planes. This is what we are often referring. So Cartesian coordinate in terms of X, Y, Z, we often come across and try to get the things done. This can be done now, everything done by graphically when you draw the molecule in software. These are all the model Z matrix or internal coordinates format. As I told you, I'm taking this one as a first reference. The carbon is connecting with the first carbon by bond length this, and the hydrogen is connected with the second carbon and make angle with the first carbon. This is what we are trying to write. This is the internal coordinate. These are all the internal coordinates. You can get the idea about how to write the internal coordinates for ethylene molecule. Want of time, I'm going very fast. This is a model input, how to do the optimization or minimization in Gaussian. When you do the model input, if you have any doubt, you can raise and then ask me. Okay. Here I am trying to give you idea about how to do the calculation, and then I will end up with the some more test cases where we are successful in publishing the paper in well-reputed journal. Okay, these are all the directory section where the scratch file has to be saved. And then what are the memory? This is very important in order to run the calculation. And then how many processor I have sharing, and what are the functional and basis set I am using in order to optimize, and I am going to calculate both Raman and IR. This is a Cartesian coordinate. I am representing the molecule. Okay, this is another way. I am repeating the same in terms of internal coordinates for water, as I told you. Okay, now I'm just submitting the calculation in a Gaussian program, what I am having the license, and then you can see these are all the, when you submit the initial calculation, there are 4 thresholds has to be followed. What are the force and the root mean square of that force and their displacement? This has to be met out. These 4 items has to be meet out the threshold value. Once it is done, the energy, you get the molecule optimized molecule. After 3 steps, that means I'm having the much closer geometry. I got the 4, yes, yes, my molecule is optimized. Yes, I got the energy, prints out the optimized geometry. Now, whether it is a global minima or local minima, how to identify? Because there are a lot of minimum, as I shown just 5 slides ago, in which you can see lot of minima among the potential energy surface. There are lot of minima. There are lot of landing points where you can land, but which is the global minimum among the all the minimum? In order to do that, we need to do the vibrational calculations. Where, as I told you in earlier case, where vibrational frequency, you can calculate the n number of frequency based on total degrees of vibrational freedom. That is nothing but 3n minus 6, 3n minus 5 for linear molecule. This is always, all the chemists aware of these information. Okay, I'm going to calculate according to the Hooke's law, the famous assumption, the model which is taken harmonic oscillator. Based on that, we solved the equation and we got the energy, nothing but V plus of H nu. That is a 0 point energy. Even at the 0 level, the molecule can vibrate. That's what ice can have the vibrational degrees of freedom. And also it is having the residual entropy even at 0 Kelvin because of this 0 point energy. So these are all the basis of quantum chemistry. Now I have calculated some of the molecules and tried to compute all possible degrees of freedom. You can see in terms of HCl, you can take 2 atoms, that is 3n minus 5. Obviously, there will be a 6 minus 5, 2 atom, so 1. Only 1 vibration I am getting. But if you take water, there will be a 3n minus 6. Okay, there are 3 atoms, 9 minus 6, 3. I am getting 3 vibrations. You can see there are stretching, there are asymmetric stretching, bending, rocking, everything. When you come to the CO2, CO2 is a linear molecule, as you know very well. It is very good example for mutual exclusion principle, where those vibrations are IR active, they are not Raman active. Okay, so there are 3 atoms, as you know, 3 minus 3 is 6, 6 minus 5, sorry, 9 minus 5, there are 4 vibrations, but out of 4, only 2 are having the change in dipole moment. You can see that there is a dipole moment change, but when you take other 2 vibrations, they are not IR active, they are Raman active. Okay, so these are all the final test case where 3n minus 6 ammonia, there are 4 atoms, 12 minus 6, 6. Obviously, you can see there are 3 vibration, only IR active. The remaining vibrations are not active because they doesn't have the dipole moment change. So now, when you do the calculation, first one, you got the optimization. You optimized your molecule. Yes, I have the energy. Very nice. Then I confirmed that it is a minimum. Yes. Among the minimum, you have n number of only one confirmation you have. Yes. But out of n number, which is the most minimum, in order to do that, we need to do the conformational analysis. That is nothing but potential energy surface scan. Everyone is studied in your MSc. When you study the stereochemistry, cyclohexane, ethane, butane, dichloroethane, those molecules you studied the conformational isomerism, especially eclipsed, staggered, anti-staggered, everything. Okay, in order to make sure that how to do the conformational analysis, we can do the potential energy surface scan by using the 4 bonds which is responsible for rotating, and then we fixed those bonds and then 360-degree take and performing the scan each 10 degree. In order to do that, I'm fixing this so that mod redundant, and then I'm performing the scan. I got the scan energy. Okay, these are all the geometrical representation. These are all available in the website. You can go through any online program. You can get these information. Yes. Then once you got the result, you can get the three minima, three maxima and four minimas. Out of this, two minima are same. These two are global minima. Okay. So now you can see exactly what is a conformational profile. You can see all kind of information you got. Very nice. Okay. Now you can see, as I told you, this is the most stable geometry. This doesn't have the negative imaginary frequency. This is a minimum energy. Okay. You can see this is the saddle point. This is not the minimum. So which is having the 67 I represent imaginary. That is mean minus 67. That means this is not the minimum molecule. You could not take this geometry for your property calculation. If you take this geometry, ultimately you will not get the right or correct experimental observation. So as I mentioned earlier, sorry, this is the one you can see here. Global minimum is greater than 0. Maxima or saddle point less than 0. The second order frequency. The first order is the energy. Second order is the vibrational energy in terms of displacement. These are all simple. You know, dou E by dou R. Dou E by dou R will give energy. Variation of energy with respect to distance. When you do the double derivative of this, that will give the frequency. That is a force. Okay. Now, I got the geometry. I got the global minimum. Yes. The next one, all are expecting why the Jacob is not talking about the UV, because this conference is all about photovoltaic 360. As I know very well. When you talk about molecular UV spectroscopy or ultraviolet visible spectroscopy, everything which is based on orbital. Especially the people are very much interested to know which orbitals is involved in the particular transition, especially electronic transition. That's very important. This is what homo-lumo in benzene. You can see the pi to pi star transition, which is happening here. This is a LUMO. This is a LUMO of ethyl bromide. You can see the sigma star and the sigma star orbital. And also ethyl bromide, there is a Lewis complex where we can see the Bronsted complex like geometry where the, for example, I can tell you from the electronic energy transition occur from bromine to Al atom. Okay. This is another one, iridium complex, where often the people are using this as a sensitizer, where they can try to get the idea about what are the transition which is happening here. Okay, as you know, charge transfer, a very important question in terms of CSIR as well as LMCT and MLCT, you know. If it is MLCT, obviously, metal to ligand charge transfer, so the ligand level has to be lower. If it is a LMCT, ligand energy level has to be higher in a level than the metal energy level. These are all common fundamental knowledge based on your chemistry. Okay. This is a very simple molecule, ethylene, where is the pi orbital. This looks like this is a pi star orbital. You can see here. So on-depending and bonding orbital. Okay. These are all we computed in order to show you. These are all the input which is used to compute the spectroscopic, especially UV. You can see this is a DD, that is a time-dependent density functional theory calculation. We can use a n state 20. That means we try to get the from S0 level to S1 level. There are 20 kind of transition. Out of these 20 level, which is most observed in the experimental value. This is a computed experimental theoretical spectrum for benzene and naphthalene. I'm not going to benchmark with the benzene value, benzene computed absorption with the experiment, because I'm going to do with my own work. You can see here, these are all the oscillator strength. You can see for benzene molecule, there are two oscillator strength, 236, that is a pi to pi star transition, which is much more common and which is having the highest ever, which is the most intense peak, that is what we observed here. Okay, this is the oscillator strength, like intensity, which is represented in terms of oscillator strength. Okay, how theory can useful, even you have calculated your lambda max by Fisher rule, by using all kind of rules, by adding some bonus value to the molecule or substituent. These are all the, you can see the same molecular formula but a different kind of geometry. This is where DDTFT or experiment is used to differentiate these isomers. You can see here, these isomers have the different kind of property. Okay, these are all our own work. You can see when you try to substitute in a benzamidine compound, where we can substitute a push-pull kind of nature. This is the electron donating and the electron pulling molecule, pushing electron push-pull effect, where you can see the pi to pi star transition of the parent molecule is changed by substituting nitro and amino group on the two sides of the molecule. Okay, this is the way we can tune by computing the spectral property. Okay, then this is what final flow chart when you try to do DDTFT calculations. My dear participants, I am not discussing much more on the level of theory or functional basis set into the quantum mechanical explanation, because that will not be needed. Everyone is using, but when you try to do the computation, these are all the points needed to be remembered in your mind, and try to concentrate in order to get the accurate and reliable result relative to the experiment. Okay, first one, proper molecular geometry and predict global minimum, and then find out the suitable functional and basis set by comparing with the experimental data, and then run the spectral property, whichever the reliable functional and basis set you obtained with the comparing with the calculation, and then give your insights on numbers, adapt to your needs and for publication. Okay, this is what we are going to do it. In order to do that, the first test case I'm going to show here. And also another one important information I have to tell you. People are thinking that when you combine with the DFT, okay, when you combine with the DFT, whatever the work you have, you can publish it in well-reputed journal. Not like that. Whatever I have pinpointed in the beginning, when you talk about Arun Kumar Kadiravan, I have collaborated with the Kadiravan and published nearly 20 papers in the field of optoelectronics. But only these are all the success story you know. Out of 20 papers, we have skipped more than 10 experimental work, which is not substantial in order to meet out the quality in terms of our photophysical property, either in terms of computational and experimental. What we do, we often write our part, by especially if I do the calculation for someone, I will write entirely whatever the observation in order to confront with the experimental observation. And then he wrote the experimental data completely by rationalizing his observation to meet out the requirement for the particular paper, particular journal. And then we compare with our results and we discuss and we correlate. If it is meet out with the needs of our expectation, then only we will send to the publication. Otherwise, we will leave those work in a dustbin. This is what we have. We did it. See, out of 5 years, we published 20 papers. I started with the JPCB, and the last paper I ended with the JCIM. Both papers are from American Chemical Society. Okay, don't think that if you do computation, it will publish in a well-reputed journal. You have to do how you are interpreting. That's what I'm mentioned here very clearly. give your insights on numbers, adapt it to your needs, and for publications, whatever the publication, wherever you want to publish, you have to concentrate on that. Okay. தமிழ்ல ஒரு பழமொழி இருக்கு, நாய்க்கு வாக்கப்பட்டா நாய் மாதிரி குறைக்கணும். அது மாதிரி if you try to publish in a paper, you have to dream of it and try to write and try to pinpoint exactly whatever they wanted. Okay. This is the one where pyrin based D by pi acceptor dice, that is a donor pi acceptor dice, where we try to compute molecular geometry by supporting experimental observation in the absence of X-ray geometry. And the energy level, they have computed homo-lumo energy, but we also computed energy levels, photophysical property, especially absorption and emission, and then there are properties related to light harvesting efficiency. These are all the simple molecule we have designed based on pyrin. Pyrin is that's a donor property, and then we taken the well-known pi acceptor, that is a pi linker. No, then we taken the best ever anchoring group, and we designed this molecule. 2 molecules I have designed with the help of Kadiravan. This is confronting his observation. Okay. Then the first ever step, as I told you, I have benchmarked with the experimental data, where I have used many levels and try to corroborate with the experimental data, and then whichever the functional is closer to the experiment, I have taken that functional in order to calculate the remaining properties. And then you can see here the molecular geometry. This is what, in the absence of experimental data, X-ray crystallography, we need this one. You can see upon substituting, there will be a pi linker, that is a pi alkenyl. Ultimately, the molecule become planar. So from which I can easily tell there will be ICT transition will be possible in this case. There will be a pi to pi star transition will be possible in this case. So we can see here excited state geometry, slight twist in the molecule. In the excited state, you can see the puron molecule, unit is also become planar. That is there is a slight twist in the molecular geometry. This is what very important aspect in the absence of X-ray data. Even X-ray data, we can't get these kind of information in terms of excited state. Okay, these are all both the excited state and the ground state molecule. You can see that there is a change in the dihedral angle from 141 to 177. Okay, but when you take ground PEFCC, perfectly planar, both the cases. Even the planarity slightly enhanced. Okay, this is a homo-lumo, you can see perfectly ICT, but due to the presence of this alkenyl bridge, some more electron density is delocalized on the anchoring part and the pi part. But both are ICT nature. Okay, these are all the contributions where we can calculate where the homo electron density is perfectly placed in donor, but LUMO, whereas 55% on the acceptor part. But you can see here there will be a, sorry for the color change, there will be a color change happening here. Okay, then you can see the homo-LUMO transition. There will be a perfect electron transfer where they can be LUMO to titanium dioxide, through which the molecule can anchor. Okay, then there will be a reversible binding also. These are all the observed experimental data, both we have located pi to pi star as well as the ICT. So this is where we computed all kind of information. One, we can do it, and we can see here there is a enhanced oscillator strength upon substituting the alkynyl bridge. Okay, so oscillator strength is increased from the, that means ultimately the photophysical properties of the particular PEFCC molecule is increased. These are all the computed spectrum, whatever which is present in the table. Okay, overall the planar dye PFCC explains significant photophysical and property. This is what we published in PCCP. The next one, very important recent paper, which is a pyrene-based chemosensor for picric acid sensing, fundamental to smartphone device. Okay, these are all the taken designed molecule, that is a TL18. We have chosen two different explosive, where trinitrophenol as well as dinitrophenol. Okay, you can see the molecule, the di molecule. This is exactly ICT nature ultimately, which is comes under. So there will be a HOMO to LUMO. There will be a pi to pi star kind of transition. And then when you see here, we have taken both interaction, how the sensing is taking place with the di molecule. We have come across so many options. You can see there are so many options we tried. That is a pi-pi stacking, OH N hydrogen bonding, CHO hydrogen bonding interaction, and also there will be a pi-pi stacking. But out of which is the lowest energy? We are not taking the final geometry as you see here. Only one geometry I tried. I got the only one geometry. That's not like case. Where we have considered all kind of possibility. In order to do that, we submitted nearly 20 cases, 20 kind of input. Out of this, I entered 4 successful story and tried to investigate what are the interaction available with this di and explosive, and we found that there are 4 interactions. And then we taken all the 4 and we found which is most stable one. I have taken this, and then I have done the aim calculation in order to confirm the presence of hydrogen bonding and quantify the nature of hydrogen bonding interaction. This is apart from X-ray, aim software, atoms in molecule. By plotting the density within the atoms, how far the density is located within the particular bond, we calculated with the aim, with the help of Q2 aim calculation. And then this is a software aim 2000. We will able to identify the nature of intermolecular hydrogen bonding interaction, and then we quantify them and we support. These are all the pi to pi star transition, which is responsible by stabilizing the picric acid with the di. Okay, so this is again the same picture, the aim picture, where you can see the which of the electrons or nucleus which is involved, s orbital or p orbital of oxygen, nitrogen 2p orbital of nitrogen, which is involved in the things. These plot can be, this is known as Laplacian graph, this is known as molecular graph. Okay, this paper is recently published in Analytical Chemistry 2019, which is a very and also the Kadiravan designed for a smartphone, how the sensor can be easily sense the picric acid. Okay, this is a purely theoretical design. That, as you are well aware of, that triphenylamine is the best donor molecule and the best acceptor, that is acrylic anchoring group, that is acrylic acid, cyanoacrylic acid. These are all the various pi linker we have chosen and try to find out the molecular property or photophysical properties of these molecules. And then as I mentioned here, as a routine work, we will do the benchmarking and try to know which level is clearly corroborating with the experimental data. Here we can see here the PBE MO62X is exactly pinpointing the experimental data, and also how far this molecule become planar when you change the different kind of pi linker. You can see alkenyl pi linker have better planarity than the reduced homolumum gap more than the aromatic pi linker. Puron based DPA, that is in that case you can see we have changed the puron as I mentioned earlier, as well as thiophene. Among puron and thiophene, puron is found to have the better planarity. As you know, the better planarity, which is having the lowest homolumum gap, which is having the highest absorption value. Here also you can find the same kind of observation. These are all the HOMO-LUMO picture from which you can see here ICT is perfectly clearly indicated in the parent molecule. But when you increase the pi linker, ultimately there will be a more kind of contribution in the HOMO and LUMO gap, where the pi linkers can be provide the delocalization ability, so that there will be a chance of delocalizing the electron density from the donor to entire molecule. This, as I told you, you can see here, there is a huge number of possibility in order to delocalize the molecule in terms of acceptor. The acceptor electron densities remain same, but the HOMO electron density, that is the electron density which is located on the donor, which is substantially reduced, and there will be an enhancement in the PTT, that is a benzothiazole unit. These are all the lower HOMO-LUMO gap. Obviously, it has the highest lambda max in the spectrum. You can see the highest lambda max value associated with the furon and the alkenyl bridge. Okay, these are all the emission. Highly emissive, as you have the high light harvesting value. As you know, these are all the better hole and the electron transport property. And as well as the electron reorganization energy is also higher. So these are all the results as I have already discussed. This is published in PCCP. This is the first ever theoretical paper, pure theoretical paper based on the experimental observation. The last ever things, this is my basic, my favorite area where I am often interested to do reaction modeling. You know, there will be a simple molecule, you know. I can show from here. You can see this is a molecule that is a salicylidine phenylenediamine. Salicylidine phenylenediamine, where we have taken this and then we try to find out the ketoenol tautomerism, that in which there will be a ESIPT, that is a excited state intramolecular proton transfer, as well as the ground state intermolecular proton transfer. Okay, these intramolecular proton transfer, how far, this is very important. This is one of the active field where the people are often working in this particular field and try to find out the reaction modeling. Okay, these are all the geometrical property. You know, we computed both the excited state and the ground state and comparing this kind of information, and we compare the OH stretching, you know, because the keto become enol become keto. So obviously there will be a change in the stretching frequency of oxygen and hydrogen OH bond. So we are monitoring both OH stretching in both the excited state and the ground state. We can see there is an enhancement in the stretching frequency of substituted molecule upon comparing with the non-substituted molecule. Okay, so these are all the excited state property. I am not going into the detail. My aim is to pinpoint how to do the DDTFT calculation in order to support the experimental observation. Okay, that's what I'm just showing the some of the successful story. Here you can see again the geometry, how far this molecule become planar when you substitute different kind of substituents. You can see the how far the excited state geometry parameter is changed in terms of varying the different solvent. Okay, then we have computed the all kind of absorption property in terms of three forms: EE form, KE form, KK form. That is a enol, keto, keto form. And then the same emission. Then there will be, you can see from here, the HOMO-LUMO transition. You can see there will be a pi to pi star transition, but there will be a transition. The push-pull effect is predominantly enhancing the delocalization, especially this particular delocalization is enhanced in the excited state of keto, methanol and acetonitrile solvent. These are all the transit state we have computed. The proton transfer modeling we have done, and then that can be also completed in all kind of solvents, 3 different solvents, and try to find out the more energetic aspects. So put together, you know, particular functional You know, this paper took lot of time. One of my student did a MSc project. This is a MSc project of one of my student. He did the MSc in 2016, but recently we published this paper because we had a lot of painful stories. That's why we took lot of analysis in this particular paper and tried to satisfy the need of reviewer, and we got the satisfied result with among the reviewers, nearly 4 reviewers, and finally we got into the successful publication in JCIM, Journal of Chemical Information and Modeling. You know, this even the title itself the matter. When you first ever we submitted to JPCA, we got the different story in 2018. Afterwards, we took nearly 2 years to write specifically and try to publish in a ACS again. Okay, this is what I try to convince you. Okay, these are all my students who worked hard in the field of photophysics, where this fellow is Johnny Brito. He was working in the particular ESCPT process, you know, his MSc project. Funny, he did a lot of calculation in terms of establishing my research interest in optoelectronic materials. Especially, he had a lot of paper in PCCP. And Deeban is also a very sincere student of mine. He is excellent in doing all kind of calculations. When we compare with all the other students, they are all equally well talented. They are well trained in terms of doing the theoretical calculation. I am very much gifted by having all the 4 students. This is a Jagan. Okay, this is my server where I have installed in Laila College. This is my lab where this is a workplace of mine. Okay. So finally, there's a time to thank my guide, my mentor, everything, and as well as this, as you are aware of this, Peter Komba is my foreign supervisor, where I did 3 of my thesis work in Germany. He is a role model. He is evergreen in my life. Without his presence, I am nothing in today. Whatever I am doing in terms of DFT calculation, he is my role model. He is the inspiration of whatever I am today. I thank Rajaraman Anna. And also Magesh Sundarajan is a scientific officer in BARC. He is also one of my senior. I inspired from them whatever I am doing today based on this. This is a Vijay Solomon. He is my junior. He did PhD in optoelectronic material. Okay. These are all my experimental collaborator, Dr. Mail Murugan. I often doing some calculation for him in order to complete bioinorganic chemistry. He is an organometallic chemist. He's working in Government Arts College, Dharmaburi. With his collaboration, I have published more than 4 papers. And then Dr. A. Kadiravan, as you're aware of that, I already dedicated, and Sangaralingam. Through him, I wrote one book in small molecular activation in RSC chemical model. Thank you, one and all present here. I hope I satisfied the photovoltaic 360 expectation, and whoever present here, they learned something how to do the theoretical calculation when you try to model optoelectronic material. Thank you for listening. Once again, I thank organizer for giving me the opportunity, especially to Dr. Mariada Asa Jonsi for giving me this opportunity to share my experience. Thank you, one and all again.
Thank you, Dr. Madhavan Jacob, for such a wonderful session. Exactly, you have covered 1.5 hours of session. It's like mesmerizing. At the outset, I would like to introduce Dr. Jacob. I'm really happy to share this information here. He's my direct senior of MSc Chemistry. We did our postgraduate course in Raja Sarpoji Government College, Tanjavur. So I just remember Professor Ramalingam sir and Professor Venuvanalingam sir in this occasion. Dr. Jacob, when you are talking, it's reminding me, Professor Ramalingam sir and Venulingam sir. Thank you so much. And if you have started with the basic fundamentals of the computational, why it is structured, what is the phenomena behind what the electrons are doing in a molecule, and you have compared the theory versus model with the cat example. That is amazing. And what is a model, and what is the accuracy of the theoretical values are highly related to the size of the molecule. That is very important. And the Cartesian's coordinates and the internal coordinates, and you have extended your and move to the high level talk, the vibrational frequency calculations, and the most important ultraviolet visible spectroscopic DFT related calculation to gain the information related to the EG band gap of every molecule, which is very, very important, highly related to this webinar like photovoltaic. We know that whenever we are choosing any molecule, the first and foremost thing is we look into that in what the wavelength maxima the molecule is absorbing, because that is the foremost important thing in a photovoltaic device. So that you have covered well. I think in general, most of the research scholars, they feel like the theoretical studies and DFT calculations are all not user friendly. It's difficult to understand like that. But today, I think our participants should have been enlightened by your talk to feel like theoretical studies also, it's very simple and easy if we understand properly. I hope everyone will start doing their own DFT calculations. It seems. Thank you very much for the wonderful session. Starting
Any
from the
questions?
yeah. I'll hand over the session to the moderator of this today's webinar, Dr. K. Karthikeyan, Assistant Professor Senior Grade of our department. He will moderate this session. Karthikeyan, sir, please.
Yes, ma'am. Thank you, ma'am. Thank you so much, ma'am. I think, good evening, sir, Jacob. I know Jacob from 2012 from NIT Tiruchi. So we are working there for ad hoc faculty. Very nice presentation, sir. So I have here some questions from participant. I can read out. The first question from Dr. Sai Rekha. For neutral molecule, we used to take 0 as a charge. And how to calculate multiplicity for our molecule? Maybe that molecules.
Yeah, sorry. Actually, I thought of discussing that one, but I forget to do that. Okay, no problem. For example, when you do any calculation, my screen is visible.
Yes, sir. Yes, sir. Yes, sir.
Okay. When you take any normal molecule, you know, 1 minute. Yeah. When you take any molecule, obviously the spin multiplicity is based on 2s plus 1. That is a number of unpaired electron. But if it is there is no unpaired electron, obviously it would be comes under 1. No, there is no unpaired electron, 0. So obviously this 0, 1. It is a neutral charge, multiplicity. Okay. When you use any metal system, for example, if you say iron 4 or iron 4. So iron 4 is nothing but 3d6 4s2, that is a 26 electron. Okay. So sorry for poor writing because I'm using mouse and not connecting with the pen. Okay. If it is 4, obviously 4 electron. You remove 4 electron out of it and then you will get the only 4 electron, 2 plus 2, 4 remaining. So you consider all possibilities. For example, it is 4, there will be a 5. Okay. Multiplicity is 5. Then if it is, there are 2 unpaired electron. Yes. Is it possible? So 3. And there will be a no unpaired electron. Yes. It is also possible still. So 0, 1. 0. 1. So 5, 3, 1. That is a quintet, triplet, singlet. That can be done. Okay. But if charge is 4 plus, so obviously you can give 4, 5, and also you have to compute 4, 3. Also you have to compute 4, 1. Out of this, once you got the calculation end, you have the energy. and try to compare the energy, which is the lowest energy, which is having the minimum energy, that is the ground state. This is often we have to do. Are you very clear? This is a normal way of considering the spin multiplicity.
Yes, sir. Thank you, sir.
Okay.
Next question, Jacob. Sir.
Hmm.
In what way DFT from Kadiravan, in what way DFT will be useful in solar cells?
Oh, Kadiravan is asking me. Okay. What way DFT is useful? Already, it can be, I can give the comparison with the experimental observation, especially when you come to the molecular geometry in the absence of X-ray crystallography data. Even I showed in some of the cases where I can easily pinpoint from the homolumo itself. I can tell you what kind of transition which is taking place in this molecule. Even general chemist can do. General chemist, which is well aware of the molecular geometry, they will pinpoint exactly the pi to pi star transition will take place. Number one. Number two, I can exactly segment for this is a unit which is responsible for the particular transition. For example, ICT, where the molecule electron density is transferred from one unit to another unit in the molecule. Second. Third one, I can illustrate some of the behavior, especially for example, when you come across the energy correlating with the contributions, FMO contributions, excited state calculations, especially I can give you the geometry of the excited state calculation. Only the problem with the DFT, the mixture of solvents, mixture of solvents, we have the continuum model. What is the model? See, the reality, when you take this tablet, you put it in the water, it is completely miscible, soluble with the water. But that kind of nature, we can't do it in a computationally. What we are doing, we are assuming some kind of cavity, that is a continuum model. We are assuming, and we are treating in the continuum level, where we are just to try to give the model. We are assuming some kind of electrostatic potential value, and we try to fix the molecule inside the cavity. Feel that I am inside the water solvent medium. That's what that is a major drawback associated with when we try to compute the property related to AAE, especially one of the experimental observation where 90% of acetonitrile with 10% of water, we could not directly correlate with the experimental data, where we try to manage somewhat calculating the averaging the dielectric constant of water and acetonitrile, and try to fix this value into the continuum model and try to get the absorption property. That's where DFT could not be able to explain. In some cases, excited state calculation, DFT miserably fail. But it is depends on how far correlating with the experimental observation. That's what we did. We did some benchmark. But in the case of EACPT molecule, that paper, JCIM, I told you, that paper, what happened, the reviewer did not accept when you do the excited state proton transfer. They never accept with the level of theory, whatever we used. That's why we struggled a lot. These are all the drawbacks. Be well aware of that. Be well aware of that. What is our advantage as well as what is our drawback. Thank you, Kadiravan.
Yeah. Next question is there is any scope in perovskite research?
Sorry?
Like perovskite. Any research?
Perovskite. Yeah.
Perovskite.
It depends. Yeah. It depends on the computational facility I'm having. Because in my college, everywhere the people are, because it's having higher efficiency, more than 20%, but the organic solar cell, which is having 12.5, more than less than 12.5. That's what we achieved. Recently, they achieved more than 10. Okay, if I am wrong, the numbers may be wrong, but the efficiency of organic solar cell is much lesser than perovskite. But we can do. Only thing, it depends on the computer, whatever we are having. The resources is very important. by performing DFT calculation.
Yeah, Jacob. Next question is from Sai Rekha from TDDFT. Do we know where the transitions take place, like between Pi to Pi star or N to P star? Sir, pi to pi star transition or N to pi star transition? She asked that.
Yeah, this is simple. No, with your permission, I will share the screen because
Yes,
I
yes.
have the. Yeah, you can see here. Yeah. He is asking about N2 pi star, pi 2 pi star. I have the molecule, but I don't think so. Here you can see there will be a pi orbital. It is clearly, sorry. This is a pi orbital. 1 minute. I will share the one more PowerPoint in which I have all the orbitals I have plotted. 1 minute.
Dr. Jacob, since it is a webinar series, we can address the queries in the next day sessions also, no problem. Okay.
Anyway, these 742, no?
Yeah, we have few more questions. Few more questions.
Yeah,
That's right.
Yeah, you ask the next question. Within that, I will share the screen.
How to calculate PES using Gaussian software?
Yes. Okay.
Yes,
I have the slide, but I didn't discuss it with the want of time. But I will quickly show that one. Then they will enjoy. Ultimately, they will come to the point where we can easily. Yeah. Here you can see the for TS. Yeah. This is the one where the Gaussian view. You can see here the molecule can be drawn. My screen is visible.
Yes, visible.
Yeah, this can be built with the Gauss view. You can see here. I can. Okay, I'm going to model the transit state for 4+2 cyclotron. Okay, so you can build the molecule, and then you can. I'm quickly going now. So I'm building ethylene, yes, and butadiene. Okay. And then I am fixing the things. I can't rotate now. So you can fix exactly whatever the way the molecule can interact. So that's the way if you fix it, I'm sure that this is a possible transit state. Yes. Then I created the input. I'm changing the bond length, everything, and then try to adjust whatever the way I needed the transit state. Once it is done, I'm giving the input for the doing the calculation. Once it is done, I'm saving the input. You know how to calculate FC, TS, no eigentest, frequency, no Raman, everything I given. These are all the things which I already discussed. Okay, I'm submitting the job. Yes, job is running. After some time, the calculation is over. 1 second. It is submitted in the server. Okay, done. I'm viewing the particular transit state. You can see here the bond formation is taking place. Upon taking the bond formation, there will be a change in the bond length. You can see there will be elongation of Y bond and the shortening of formation of double bond. These are all the double bond. These two are forming the bond, and these become single bond. Okay, this is another view of the same transit state, whatever I have confirmed. Okay, now I got some kind of TS. Yes. TS is majorly confirmed with the presence of one imaginary frequency. For example, in this case, you will get the imaginary frequency in terms of minus 235. Okay. But how to make sure whether it is a right transit state or the wrong transit state? So that what we will often see, IRC, we will run the IRC calculation, and then this is a transit state, and one side, this is like a cat is sitting on the wall. The cat can go either side, either right side or left side. Similarly, we can have the transit state. It can have a n number of possibility. It can have the n number of possibility. But this transit state depends on whatever the geometry I expected, whatever the desired product I expected, whatever the reactant I chosen. So whether it meet out the same criteria, whatever I given, yes, I have to do the IRC calculation. Once I have done, I got the 2 points, TS, and I don't know whether it is reactant or product. Now I am running the calculation. Okay. At the end, we will get the output of those calculation, and you will get the, wait, I will have one more. Yeah, here I have everything. Sorry. Yeah. When you do intrinsic, you will get the product. Okay. That up to that level we have stopped. Okay. I don't have that one.
Thank you, Jacob.
Maybe
Next question is,
next
question is what are the basic softwares for DFT? Any free access available? What are the basic softwares for DFT? Basic software for DFT.
We are using Gaussian. There will be a Jaguar, which is available in the Schrödinger Masto. ADF, which is also using Amsterdam density functional software. They are all commercially we have to buy, but the people are using often. And there are other software maybe freely available, but we are using Amber, Gaussian, ADF, Jaguar. All are very well versed software developed by the US people. One from Netherlands, another one from two are from US. There are so many people, and one from Netherlands. These are all the three software we are often using for the DFT calculation. But for molecular dynamics, there are a lot of software are freely available. We can use it.
Okay. Next question is, if you do optimization, it is necessary to do conformational analysis to find global minima?
Yes, obviously, without knowing that, how do you make sure whether you are getting the right geometry or not? No. If you take the highest ever point and try to get all the property, after computing all the property, wasting your 1 month time, at the end you come to know your geometry is useless. Then all the time, whatever you spend is a waste. This has happened for me when I was doing first time metal complexes in Germany. I spent nearly 2 months. I finished the entire project. After that, I come to know that whatever the functional I have used, that is wrong. Because of that, I got the wrong energies and recomputed everything with the new function. Okay. So getting right functional on the right geometry by performing the potential energy surface scan, if it is an organic molecule, if it is an inorganic complexes, you have to do the swing state energetics and try to get the ground state geometry. Then only you have to do the other property, even TS or anything. If you take the wrong geometry, ultimately your time is waste.
Okay, last question from chat. Okay, how can we calculate intensity of IR and Raman spectra from Gaussian program?
Yeah, when you open software results, I don't have the software in this laptop. Otherwise, I will open. If you open results, this kind of vibrational spectrum data will come. Maybe I will show you. Yeah, here itself I have. Somewhere I have shown. Yeah, in Johnny work I have shown. Yes. Yeah, this is a stretching frequency. This is the intensity. There will be a IR force constant as well as there will be a IR intensity factor. The value will be much more higher. Those only will get the peak. Other than everything will be come into the waste. It will not give any peak at all, according to the 3n minus 5. When you take this molecule, there are 3, 6, 18, 20, 22, 23, 24, 25, 26, 27, 28. 3 into 28, 60, 84. 84 minus 6, 76 or 78. Obviously, 78 transition vibrations will come. Out of 78 vibration, these are all, we have narrowed down within the window of 2900 to 3400. But if we have the window, it will give all the vibration, but you will get the intensity only if you have IR active. Okay? That is the software directly will give.
Sir, in some papers, they have given one formula for calculating the intensity. Whether we want to use that formula or directly we can take the intensity from the Gaussian program.
You are talking about the scaling factor?
Yeah, yes, sir.
Scaling factor is nothing but, for example, in that case, I not scaled this value.
So whether we want to use a scaling factor or we can directly write the value from the program?
It depends on the paper you are submitting.
Okay.
Because
directly we can give... yes, sir. Yes, sir.
Yeah, wait. When you try to submit the paper,
yes, sir,
that value, for example, I'm saying, if you get the vibrational frequency around 3,400 experimentally, but you are getting around 3,700.
Yes,
you are
sir.
submitting to the reviewer. Okay. A reviewer will accept your paper. The nearly 300 difference in the computed vibrational number.
No, sir.
So, whatever the functional and basis set you are using, there will be a scaling factor. Okay. With the scaling factor, you have to take it, for example, for B3LB631G star, I remember 0.9825. Example. Okay, you have to multiply with 3,590. Is it visible with my computer?
Sir, actually it is in the hole and particle.
Yeah. If you multiply with the 3,590, you will get 3,527. That is closer to the experimental value. So that you have to give the scaled unharmonic vibrational frequency, harmonic vibrational frequency. That's what often we do. That is not for calculating the frequency. That is in order to correct our closeness to the experimental value. So that we will often use scaling factor.
Okay, sir. Okay, thank you, sir.
Okay, are you very clear?
Sir.
Yes, sir. Thank you, Jacob, sir. Ma'am, Asha, ma'am, shall I wait?
Yes, sir. Yes, sir. I think we have one more question in the chat box from Srinivasan, sir. I think so.
Yes.
I think he has asked like, if my geometry is wrong, will it optimize or not?
Okay, very easy question, very clever, as well as when you say, for example, water is bent, as you know very well. If you give water is a linear, maybe foolish, but I am asking you, if you give water is a bent, instead of bent you are giving linear, what will happen? The calculation will not run. Because what is the basics included in the software? They taken the electrostatic charge, all the things, and they put together. If you say hydrogen, if you say oxygen, there will be a valence cell electron pair repulsion. With that, the molecules become, there are two lone pair. As you know, two lone pair repulsion is much higher than lone pair, bond pair, and then bond pair, bond pair. So obviously the hydrogen will become stringed. So if you say 109, instead of 109, if you give 90, software will adjust. If you give, instead of 109, if you give 120, software will adjust. But if you go more than that, 0 or 180 or 170, obviously calculation will not run. It will be terminated due to error of 999 or 49. This is a common error in terms of giving the wrong geometry. Okay, so some intuition, that a chemical intuition, has to be applied. Without chemical knowledge, you can't do. Finally, I will conclude. Oh no, doing chemistry in computer is not easy. It is not. I'm not mistaking all the chemists. I'm just saying, before I'm going to choose any of the computational project, I have to well aware of all the experimental detail, especially geometry, solvent, what are the property, how it is stable, how what are the temperature at which is stable, everything we come to know, and then we will fix the molecular geometry, we will fix the stereochemistry, and once it is right, then only it will be submitted. Okay, so this is very important. If you are giving wrong geometry, ultimately it will not run. Thank you, sir.
Thank you, Dr. Jacob, for the wonderful session with the detailed discussion. You have addressed almost all the queries raised by the participants. I must acknowledge Dr. K. Karthikeyan sir also for moderating this session. I thank Dr. Sajan sir for introducing the resource person today. So this is for the, thank you, Jacob. No.
Thank you, Asha.
Yeah.
Karthi, thank you. Nice to see you after so many.
Yes.
This is the information to all the participants. Already we have shared the attendance link for today's session. It is working and we are receiving the responses from the participants. Please check it and fill it. It will be open in another 15 minutes. And this is the information to the participants regarding the tomorrow's session. The day 4 of Photovoltaics 360. The speaker is Professor Dr. R. Kodandaraman sir, Professor of Chemistry, Indian Institute of Technology, Madras. He is going to talk in the topic of understanding the role of CDCA in tandem with the pi spacer in dye-sensitized solar cells. I would like to mention I am working with Professor for my ongoing TAR project, Teachers Associateship for Research Excellence. So, sir will show you the live demonstration of the fabrication of the devices in large scale, and he will cover the most of the how the different components of the photovoltaic cell is going to be give it input to the device efficiency. So the chairperson and the moderator for tomorrow's session are Dr. Revati Purushothaman, Associate Professor, and Dr. K. Shakila, Assistant Professor of our department, BSA Crescent Institute of Science and Technology. So with this, Professor Kerar. Yeah, I would like to thank everyone in the today's session who are all participated and enlightened by the theoretical inputs of DFT calculations related to the photovoltaics. Thank you so much. Sir, HOD sir, can we conclude?
Asha?
Yes, sir. You are audible, sir. Please.
Thank you. Dr. Jacob has left or is here?
Yes, sir is there.
Sir, I am here only.